Hello, everybody. My name is Theoni Karlesi from University of Athens, Greece, and I would like to thank very much Maria Kolokotroni for this invitation to the men's short course about nearly zero energy building retrofit. Let me just say a few words in advance concerning the Smart Gems Energy Network project that was the occasion, let's say, for this presentation and this cooperation. So the project has to do with smart grids and smart systems, dynamic and interactive real-time infrastructure, integrating electrical and IT technologies, matching of generation and consumption, smart monitoring and control, load shaping, energy saving, energy efficiency and optimal integration, reliability, and diverse of stakeholders. Smart Gems project is a coherent training and research project that focuses on the design and optimization of real-scale smart grid applications and innovation through staff and know-how exchange between universities, between educational institutes and industrial partnership. So just a few words about the scope and objectives is to develop a strong and sustainable synergies between academic community and industry experts, to transform innovative ideas into solutions, to draw coherent methodology for the development of smart grid applications, transfer knowledge and build new and complementary competencies, investigate and disseminate advanced practices and modern techniques, foster process and product innovation, promote business initiatives and develop career opportunities through research and development activities. So a project approach is to focus on smart grids and zero energy building analysis and examine users, consumers aspects, investigate various smart grid components in order to expand the cycle of the smart grid penetration to community or to city level. Hi, Maria. I'm hearing some noise now.
No, sorry. Me.
Yeah.
Okay. Actually, it does not work with the two computers. That's the problem. We're okay now.
Okay, I can continue, or should I start from the beginning? Was I heard before?
You can continue. I'm outside the room.
Okay, good. And integration of components targeting to the development of smart applications and IP connectivity to optimize smart grid performance. So this is just an overview of the project, and now I think that we could proceed and start with the presentation, which has to do with smart communities and innovative 2.0 in order to have this approach in the building sector in Europe and to minimize the energy consumption, to eradicate the energy poverty and mitigate the local climate change. Just a second, because... Okay, so the contents of the presentation is concerning the development of smart and zero energy building protocols for Europe with the objectives, which has to do with the analysis and identifications of three major problems of the built environment, which are the energy consumption, the energy poverty, and the local climate change and the synergies between them, a set of a roadmap involving future quantitative and qualitative targets, investigating the major technological, economic, and social forces and policies to identify what are the links, the synergies, and the impacts, and the interrelated nature and characteristics of these three sectors, and the benefits for the society, including the impact on the economy, the employment, the environment, and health, and, of course, a list of conclusions. So concerning the development of smart and nearly zero energy protocols for Europe, The three major problems, as we mentioned also before, is the high energy consumption, the local climate change, and the energy poverty. Just a few words about the situation, which is that the buildings consume almost 9 petawatt-hours and represent 41% of the total energy consumption. The total European building stock is close to 24 billion square meters, and almost 75% of them are residential buildings with an average floor space which is close to 87 square meters per dwelling, while the rest is tertiary buildings. Almost 27% of the total energy consumption in Europe is spent by residential buildings, while the rest, 14%, is consumed by the tertiary sector. The average building energy consumption in the European Union countries varies between 320 kilowatt-hours per square meter yearly in Finland and 150 kilowatt-hours square meter per year in Bulgaria and Spain, while a mean value is close to 220 kilowatt-hours per square meter per year. So there are large differences in the energy consumption between residential and tertiary buildings. Dwellings consume on average almost 200 kilowatt-hours per square meter yearly, while the mean consumption of the non-residential buildings is close to 295 kilowatt-hours per square meter per year. The energy consumption in tertiary buildings is increasing constantly. The energy consumption of this sector has a constant increase during the last 30 years. The increase rate is 1.1% for the years between 2010 and 2020, and this increase of this energy demand is because of the evolution of the services sector that increased by 1.3% per year. Of course, services will be responsible for a major percentage of the additional energy to be consumed by the tertiary buildings between 2000 and 2030. Trade and office buildings are the largest energy consumers, accounting each one for about 26% of the global consumption for this kind of buildings, while the space heating seems to be the end use presenting the higher energy consumption. And energy spent for heating presents, let's say, a constant decrease over time, and this is a result of an important energy conservation measures that is applied in tertiary buildings, and this is something which is rather optimistic. So the energy consumption of the residential buildings is increasing constantly, and this is despite the strict legislative framework and the significant improvement of the energy efficiency. The energy consumption of the residential buildings between 1990 and 2020 has increased by 14%. The electricity used increased by 60% because of the very rapid penetration of electronic appliances and services, and the final energy consumption in the residential sector in the European Union was had a major number in 2010, while there was a slight reduction while the responding consumption for the year 1990 was reduced. Was lower, let's say. So this increase of the energy consumption is mainly attributed to various economic, social, political, and technical reasons, and this is, of course, mainly due to the increase of the number of households and the increase of the occupied space per person. So the energy consumption for heating is decreasing constantly. Although the total energy consumption of buildings has increased, the specific consumption for heating purposes has decreased to about 15% during the period of 1997 and 2009. And this is maybe attributed to the considerably lower consumption of the new dwellings, which are built after 1997 and represent almost 20% of the total dwelling stock in 2009. The new dwellings consume almost 30 to 60% less thermal energy than houses that are built before 1990. Let's say dwellings built in 2009 in Germany present almost 58% less energy consumption than those built in 1990. And the corresponding energy reductions in Sweden, Denmark, Slovakia, and the Netherlands are 55%. It's between 55%, let's say, until up to or down to 50%. The impact of the economy on the energy consumption in buildings and the energy consumption in the building sector is subject to significant economic, environmental, and social factors and perturbations. Past and present experience demonstrate that this is an extremely sensitive sector which presents a high variability in economic and environmental variations. Financial problems that oblige part of the population to consume less energy and satisfy partly their needs. And it is characteristic that during the financial crisis of 2007 and 2012, the energy consumption of the residential buildings was decreased by 4%, while in countries with a deeper economical problem like Portugal, Slovakia, or Ireland, the decrease was even more. It was 16, 22, and 22 respectively. And it is characteristic that because of these serious economic problems, in Greece, the consumption of the heating oil was reduced by 68.7% in just 1 year. There were many situations and many residential buildings in Greece that during winter time the most of the parts of the residential buildings did not have heating at all because they could not pay for the heating oil. Concerning the factor of local and global climate change, which has a very serious impact on, of course, the energy balance of Europe, climate change is a major issue. Increase of the ambient temperature and higher frequency of heat waves have an important impact on the energy and environmental quality of the built environment and increase the vulnerability of the local population. Given that 74% of the European population live in urban zones, urban climatic conditions and local urban climate change affect a very significant part of the European population and have serious impact on the global energy and environmental quality of the built environment. And, of course, higher urban temperatures increase the energy consumption for cooling and raise the concentration of pollutants, deteriorate thermal comfort conditions, and create important health problems to vulnerable populations. This diagram shows, let's say, the measured annual average maximum and absolute maximum urban heat island intensity for several experiments based on the use of standard fixed meteorological stations. We can see that let's say the annual average urban heat island intensity varies between 0.1 and 2 Kelvin, 2 degrees of Kelvin, with an average close to 1.08 And the average maximum values, we see that varies between 0.3 and 6.8 Kelvin, with an average close to 2.6. While the absolute maximums are between 2.8 and 12 degrees of Kelvin, with an average about 6.2. So we can see important values here of the urban heat island intensity levels. With different scenarios that were estimated, we can see a forecast of cooling degree days of 26 of a level of 26 Celsius, and the trends on the impact of energy between 1960 and 2100, which shows a very clear and very important increase. Here in this diagram, we can see some estimations and some correlations between in several studies that were implemented between the temperatures and the mortality rate. Mortality rates in low-income households, which are exposed to extreme weather conditions, either too cold or too hot, are found to be much higher than in the average population. And there are several studies that prove this. These studies have concluded that the households with we could say low socioeconomic status, living in poor houses, of course face a much higher heat-related excess mortality. And despite, of course, the progress that has been achieved during the last years, still there is a very high number of excess winter also deaths because of the low indoor temperatures during the winter period. There is a study that has reported, and this could be available. I can distribute the related publications to this, and of course the related publication for this presentation that I'm doing. They reported that they are about from, let's say, 30,000 up to 60,000 excess winter deaths annually in the UK because of the cold homes, while mortality rates vary as a function also of the housing quality. Excuse me. And this can be related to the general threat for Europe concerning the energy poverty. Energy poverty is, with a rough definition, is the situation in which a household lacks a socially and materially necessitated level of energy services in the home, or in much simple words, when one cannot pay the bills for the essential services for lighting or for heating of the house. It is a problem of over 150 million Europeans, which they cannot afford to pay the bills and maintain the comfortable standards. And this is particularly valid for the citizens of the state with a GDP below the EU average, where over 30% of the population face energy poverty. This fact has a very serious impact on the quality of life of the citizens, affecting indoor comfort conditions, social attainment, and health. And it is a result of combined factors like the insufficient family income, the poor quality and the low size of the house, and the possible, of course, high energy prices, while, of course, other demographic drivers may play an important role. low-income population lives in poor energy performance houses. According to the European statistical data, almost 10% of the European Union population live in houses with important energy and environmental problems, while the corresponding percentage increases to 25% for the low-income groups. Other data reveal that about 20 to 55% of lower-income households in Eastern and Southern European countries live in dwellings with leaking windows. In the UK, about 17% of the poorest families live in houses with serious disrepair, while low-income population lives in dwelling with mold and condensation, 3 times more likely the high-income population. In parallel, there are almost a quite important number of houses which are suffering from excess cold, which is about the 8% of the dwelling stock in the UK. And now we can, as I mentioned in the introduction, we will try to define some synergies and trade-off between low energy consumption buildings and decrease of the energy consumption and the global and local climate change. So we can see that this figure is trying to introduce a comprehensive view of these specific interconnections and influences. So, as shown, a decrease of the energy consumption of buildings, of course, influences global and local climate change through these 3 precise links, while climate change may influence the energy consumption of buildings through other specific casualties. So, in specific, trying to identify the synergies and the impacts between the low energy consumption and the local climate change, because, of course, there are also other interconnections that I will just focus on this. There are, of course, other interconnections between low energy consumption and energy poverty, or energy poverty and climate change. But this, you could see it in more detail in the publications, because I don't want to confuse you much with this presentation, and we have also a time limit, so I will try to just underline some major factors. So one major link is the low energy consumption decreases. The low energy consumption decreases heat emissions from HVAC systems and power plants, and reduces the total anthropogenic heat and CO2 emissions released in the atmosphere. Another link is the increase of the energy efficiency of buildings that will decrease the cost of energy services, and this may result in an increase of the consumption, which is, let's say, it is called the rebound effect. Another link has to do with the fuel shift from conventional to renewable energy sources that will result to decreased gas emissions. Moving forward, the higher ambient temperatures increase the energy consumption for cooling and decrease the energy for heating, while higher ambient temperatures and heat waves increase the peak electricity demand and oblige utilities to build additional power plants operating for reduced time periods, which is something that is very important and is very consuming and needs very much the attention. And also, they oblige, the peak loads oblige for additional electricity transmission infrastructures, and there is, of course, this of course results in increased cost of supply energy. Another link has to do with the climate change that creates increased energy and environmental needs for dwelling of the elderly and vulnerable population, which is also socioeconomic aspect that needs attention. Of course, also we have the urban heat island, which increases the size of the HVAC systems and raises the capital investment costs. Also, urban heat island increases the concentrations of ozone in the atmosphere and obliges for additional mechanical filtration and ventilation systems. Something good and something very optimistic that I think that we all heard these last days is that the ozone hole is, there were some evidence and some studies that proved that the ozone hole was reduced. So this is something very good. Another link has to do with higher ambient temperatures that decrease the potential of passive cooling techniques like night ventilation. So this has to do with, these synergies has to do with these two interconnections. So moving from innovative to zero, zero energy consumption, zero climate change, and zero energy poverty, which is a goal that we will all want with this and with all combined actions to achieve. This idea of a future zero concept world involves an innovation to zero strategy, of course, for all technologies that are related to emissions, wastes, defects, etc. The ultimate goal of this whole concept is to develop zero emission and zero waste technologies applied to zero energy and zero emission buildings and cities, where advanced and innovative technologies and policies will be applied to minimize other, of course, social factors. Although such a concept seems to be very radical and perhaps it could be seen as opportunistic, the idea incorporates some exceptional features of a development roadmap that makes it particularly attractive and, of course, essential. So, setting the future goals regarding the energy consumption of buildings, the impact of the construction sector on the local climate change, and the possible levels of energy poverty to zero is choice unequivocal. Mankind needs an ambition, visions to proceed, and this should be clear, and it should be clear the set of future goals that, of course, will be achieved gradually. So even the attainment and the satisfaction of some of these goals will be a major success and progress for the societies. The adoption and achievement of the specific objectives require planning and follow of an innovative scientific and political agenda, which should include technological breakthroughs. So this involves significant investment in the construction sector, which will create substantial opportunities for the future and will certainly cause major, medium, and long-term benefits for the society, while alleviating the population by the intensity and the consequence of particular problems. Here, this figure presents, let's say, in a comparative way, the characteristics and the results of 16 energy conservation scenarios for 2050 as proposed by the European Commission and by some other organizations. This figure reports the foreseen cumulative investment costs until 2050 as a function of an achieved energy conservation, which is represented by the width of the circle, and the calculated investment cost per petawatt hour of energy conservation. And this is the cost for $1 trillion USD per petawatt hour. And this is a diagram of cost similar to the previous for the energy conservation. This cumulative investments to almost minimize the energy consumption of the building sector in Europe by 2050 should be between 14.5 to 23.6 trillion of euros. The CO2 emissions of the residential sector in 2050 will be reduced by 90.3 compared to 2005, while the corresponding decrease of the tertiary sector is close to 87.7%. The application of energy efficiency measures has a positive effect, of course, on employment and the number of additional full-time jobs created in Europe per 1 million of euros invested, and varies between 6.4 and to 39, with an average value close to 18.9 jobs per million of euros invested. Here is let's say, a summary that has to do with the policies and different actions, the required investments and the corresponding energy reduction, the full-time jobs annually created, and other benefits. These are the information that has to do with the action of minimizing the energy consumption for the building sector with the different scenarios for the period of 2007 to 2050. So policies aiming to minimize the energy consumption of buildings should concentrate of three main technological axes that aims, firstly, to increase the global energy efficiency of the building energy systems in order to seriously decrease the energy load and the final needs, to supply the remaining energy load through clean and renewable technologies, and to optimize the management of the energy and environmental systems of the buildings through the use of smart and intelligent technologies. Intensive research has permitted to develop technologies that help to mitigate and minimize the amplitude of the local climate change. Among the most promising technologies are those aiming to increase the albedo of cities, highly reflective materials used in roofs and or in pavements in order to reflect the solar radiation and avoid the absorption of solar heat, are the technologies which are known as cool roofs and cool pavements, respectively. A variety of these highly advanced reflective coatings and materials has been developed, presenting very high reflectivity in the solar spectrum together with a high emissivity value. And cool roof systems are extensively used around the world, and their capacity to mitigate the urban heat island is well documented. What we can see here is the calculated financial investments to install the proposed cool roofs and pavements in each considered city, in different cities. The total estimated cost to implement cool roof in the selected European cities as an average is close, let's say, to 22.2 billion euros. While in parallel, this figure gives the calculated necessary investment per person, both for the cool roofs and the school pavements. As we can see here, the average cost of school roofs per citizen is close to 277 euros, and at the same time, the average cost per person for the school pavements varies between 970 to 70 and 1,600 roughly euros for the low and the high cost scenario, respectively. And it is evident that the calculated cost per person, of course, varies as a function of the considered total area of interventions and the population of different of the selected cities. Considering the policy or the action of the mitigating the urban heat island, we can see in this table some information considering the required investments, the energy reduction, the full-time jobs annually created, and some other benefits. Energy rehabilitation of the homes occupied by the lowest income households is the more efficient policy in order to fight the energy poverty and to protect the vulnerable population. A deep retrofitting of the building stock used by the energy poor in Europe could have very significant social, financial, and environmental advantages. To estimate the possible benefits from such a policy, the necessary investments to minimize their energy consumption as well as the existing housing conditions have to be known, or at least they have to be estimated. Given that the energy poverty is not approached in a common way in Europe, and at this time there are some actions that try to present it or even to define it in a homogeneous way, the energy poverty. There are convergent assessments about the total amount of the energy poor. So here, in this figure, what it is presented is the calculated investment cost considering different population of energy poor. 50, 125, and 150 million energy poor for all different 17 scenarios, different scenarios of refurbishment cost that is presented with different countries and different investments and different remarks for each scenario. So this is the corresponding table that has to do with the eradication of the energy poverty, concerning the required investments, the energy reduction, the jobs, and other benefits, which is also here, we can see a major benefit which has to do with the reduction of health problems. High energy consumption of the building sector, local climate change, and energy poverty are the major drivers and the major problems of the built environment in Europe. The three sectors are strongly related with each other and present very significant synergies and trade-offs. Existing policies aiming to reduce the energy consumption of the buildings usually underestimate the importance and the impact of the local and global climate change, as well as the technical, social, and economic implications related to the energy poverty. And, of course, a failure to consider all these issues as an integrated and a holistic way may inevitably result in higher consumption and in deterioration of the social and economic level. Innovating to zero the built environment of Europe assumes a minimization of the energy consumption of buildings, eradication of the energy poverty, and mitigation of the urban heat island and the local climate change. So, of course, such an objective, although it seems very ambitious, is a choice that we cannot avoid, and this will create substantial opportunities for future growth and will alleviate the population from the consequences of all these problems and create short, medium, and long benefits and opportunities for the people and for the societies. And now I have reached the end of this presentation, and I would like to thank you very much for your attendance. So, Maria, are you with us?
Okay?
Yes, I can hear you.
Yeah, actually now I'm connected with the laptop, so
Okay.
the speakers are not as good. We used to hear you very well, but now you can hear us as well.
Okay.
So we are two ways now.
Okay, that's great.
Thank you very much, Theoni, for this presentation, which I'm sure, as all of you appreciate, full of facts and also proposals, and also will give the paper afterwards for
Yes, of course, because I try to give an overview of many, as you see, of many factors and many different aspects that. Of course, for every one of us, each aspect needs much attention and much and many things to take into account, and it is quite important and difficult and important at the same time. The estimation of all these aspects, but I think it's worth this kind of studies.
Yeah, to begin with.
Yes.
So thank you. Let me ask, is there any question, please?
Maria, I suppose we're going to get the presentation and the paper, so...
You are going to... The question was about if the presentation and the paper will be given to you. And
yes, of course, it will be given, and more information, it is included in the paper, of course. And the references, because this is, of course, something very, very important to present some things, but, of course, to have some solid proof for what is presented. Yes.
There is another question, I think. Yes, please.
Yes.
Hi. The graph that showed the excess winter deaths and the excess summer deaths,
yes.
Were there any particular countries that applied to?
Excuse me, I could not hear. I cannot hear you very well about the question of the mortality. You said yes.
Which countries did that represent?
Yes, I can. There are different countries. Besides the information that I gave about UK, there are different countries from all over Europe. But I'm not. I don't remember which are the countries now. But there are countries like I think Ireland, Finland. It's Portugal, Spain, Greece, and some other countries that I will provide you the full diagram with.
Thank you.
Thank you.
Yes.
Any more questions? I think probably this is it, and they were listening intensively all the time. Me too, as well, from outside, because I had to stay outside not to have interference.
Okay.
So,
I hope it was interesting for you. I hope so.
So thank you very much.
Thank you very much, everyone, for your attendance.
So yeah, thank you, and actually for your information, because you have not seen us, we are about 35 people listening.
That's great. Okay, that's nice.
Thank you very much. Have a good afternoon.
Have a good afternoon too. Bye bye.